We built computers to get closer to the truth. That's always been the idea. Better tools, better measurements, better models of how the world works. And for a long time, that worked exactly as expected. Each new generation of technology made reality feel more solid, more predictable, more understandable. Then quantum computing showed up. At first, it looked like just another upgrade. Faster machines, new ways to solve problems that regular computers struggle with. But something strange happened as these systems improved. The more we relied on quantum behavior to compute, the more we had to accept that the rules underneath reality don't behave the way we thought they did. Not just a little different. Fundamentally different. Quantum computers don't just process information. They depend on particles being in multiple states at once. They rely on connections between particles that ignore distance. And when you actually run these systems, you're forced to deal with a possibility that sounds less like physics and more like a glitch, that the world doesn't fully exist in a definite state until something interacts with it. This isn't philosophy anymore, it's something engineers have to work with directly just to make these machines function. And that leads to an uncomfortable question. If our most advanced computers only work because reality behaves this way, what does that say about reality itself? For most of human history, reality seemed straightforward. If you look at something, it has a definite state. A ball is either here or there. A light is either on or off. Even if you don't check, you assume it still has a clear, fixed condition. That assumption is built into everything, including how classical computers work. Inside a normal computer, every bit is simple. It's either a 0 or a 1. Not both. Not in between. Just one clear value at any moment. All modern software, from games to banking systems, runs on that certainty. Quantum systems don't follow that rule. A quantum bit or qubit can exist in a combination of 0 and 1 at the same time. This isn't just a trick or a shortcut. It's how the physics actually behaves. Until you measure it, the system doesn't settle on a single answer. That's already strange, but here's where it gets uncomfortable. In classical thinking, uncertainty just means we don't know something yet. In quantum physics, uncertainty can mean the property itself isn't fully decided. Quantum computers take advantage of this. When they run calculations, they don't try one possibility at a time. They operate across many possible states at once, using interference to push the system toward a useful answer. But to make that work, you have to accept something deeper. The computer isn't just exploring possibilities, it's built on a version of reality where those possibilities are all physically meaningful at the same time. And the moment you measure the result, all of that collapses into a single outcome. So before measurement, what exactly was real? Superposition is already hard to accept. Entanglement takes it further. When two particles become entangled, they stop behaving like separate objects. Instead, they act like parts of a single system, even if you move them far apart. Change one and the other reflects that change instantly, not faster than light in a way you can use to send messages, but fast enough to break something deeper, the idea that things only depend on their immediate surroundings. This is where Bell's theorem comes in. In simple terms, Bell showed that if reality were truly local and particles had pre-existing properties, then certain statistical patterns should always appear in experiments. But when physicists actually ran those experiments, the results didn't match. Over and over again, the universe violated those limits. That means at least one of our basic assumptions has to go. Either information isn't confined by space in the way we expect, or particles don't have definite properties until they're measured. Quantum computers don't just observe this effect, they rely on it. Inside these machines, qubits are entangled on purpose. Their states are linked so tightly that you can't fully describe one without the others. The computation spreads across the whole system, not as separate steps, but as a single connected process. Engineers don't get to ignore the weirdness. If entanglement breaks, the computation fails. So this isn't an abstract puzzle anymore. Our best working technology depends on a version of reality where distance doesn't fully separate things, and where the idea of independent, self-contained objects starts to fall apart. At some point, this stopped being theory and started becoming engineering. Companies like Google and IBM built quantum processors not just to explore ideas, but to run real computations. And when they did, they ran into a strange situation. The machines were producing results that classical computers couldn't realistically reproduce. In October 2019, Google announced a milestone called quantum supremacy. Their processor completed a specific calculation in minutes that would take the most powerful classical supercomputers an impractical amount of time. Not because the task was useful, but because it exposed a gap. A clear separation between what classical systems can simulate and what quantum systems naturally do. That gap matters. If a classical computer can't simulate a system, it means our usual way of describing reality starts to break down at that level. We can predict outcomes statistically, but we can't track every underlying step in a familiar cause and effect way. Quantum computers also generate randomness that appears fundamentally irreducible, not just unpredictable because of complexity, but unpredictable in principle. Some experiments even use quantum processors to certify randomness, meaning no hidden classical process could have produced the same result. Then there are simulations. Quantum machines are now being used to model molecules, materials, and physical systems that are too complex for classical methods. In doing so, they're not simplifying reality. They're matching its underlying rules more closely than anything we've built before. And that leads to a quiet but important shift. We're no longer just observing quantum behavior. We're building machines that operate inside it, and in some cases, reveal patterns we can't fully explain using classical logic. All of this builds toward a deeper issue that physicists have been circling for decades. What actually happens before a measurement? One of the oldest answers comes from the Copenhagen interpretation. It treats the quantum state as a set of possibilities that only becomes definite when an observation occurs. Not because we finally see it, but because the act of interaction forces a single outcome. That idea was once easy to keep. At a distance, it sounded philosophical, even optional. You could do the math, run experiments, and avoid worrying about what it means. Quantum computing makes that harder to ignore. These machines depend on fragile quantum states staying unmeasured long enough to perform a calculation. The moment unwanted interaction creeps in, the system loses coherence. The possibilities collapse and the computation falls apart. So engineers spend enormous effort isolating qubits from the environment, not to protect delicate hardware, but to prevent reality from settling too soon. That's a strange thing to say out loud. It suggests that what we call a definite state isn't always there in the first place. It emerges when interaction forces the issue. There are other interpretations. Some propose branching universes. Others suggest deeper hidden structures we haven't discovered yet. But no version fully restores the simple picture most people expect, where everything has a clear state, whether we look or not. Quantum computers don't prove that reality is created by observation, but they do something almost as unsettling. They turn that possibility into a practical constraint, a rule you have to respect just to make the technology work. And that leaves us with a question that no machine can compute away. If reality only becomes definite when it's forced to, what is it doing the rest of the time? We set out to build better computers, faster ones, more powerful ones, tools that could solve problems beyond the reach of classical machines. And in doing that, we ended up building something else entirely, a device that only works if reality itself behaves in ways that don't fit our usual picture. Quantum computers don't break the laws of physics. They follow them exactly. That's the unsettling part. The strange behavior isn't a glitch in the system. It is the system. Superposition, entanglement, measurement. These aren't edge cases anymore. They're the foundation of how these machines operate, and every time a quantum processor runs successfully, it quietly confirms that the world underneath our everyday experience is still as unresolved as ever. Not because we lack the tools to measure it, but because the act of measuring might be part of what defines it. That doesn't mean reality is an illusion. It doesn't mean nothing exists until we look, but it does mean the simple, comfortable idea of a fully defined world, sitting there unchanged whether we interact with it or not, is getting harder to defend. And this shift didn't come from philosophy, it came from engineering. We built something to compute answers, and in the process it started asking its own question, one we can't ignore anymore. What does it mean for something to be real? Quantum computers just peered behind the curtain of reality, and what they saw is disturbing. Forget everything you think you know about the universe at its most fundamental level. The data reveals a flaw, a massive, potentially catastrophic flaw in our understanding of, well, everything. The evidence shows our current models are not just incomplete, but fundamentally wrong. The problem? Quantum entanglement and the simulations are showing something nobody predicted. Is reality as we perceive it even real? Prepare to question everything. The implications extend far beyond physics, 99.99%. That's the level of accuracy we demand from our simulations of reality. Anything less, and the whole thing falls apart. The problem? Quantum entanglement is spitting in the face of that accuracy. It's as if the universe has a secret handshake it refuses to show the computer. So, what does this have to do with the simulation hypothesis? Well, it's one of the leading arguments against it. Consider this. If our reality is a simulation, it's being run on some kind of computer, right? All computer, no matter how advanced, has limitations. It needs resources. It needs processing, power. And at some point, shortcuts have to be taken. Approximations made. One of the most oft-cited limitations of a simulated universe is computational power, the amount of processing power it would require. A true atom-by-atom simulation of a universe the size of ours would require, well, effectively infinite computing power. The resources are simply not there, so simulators would need to be clever. They'd optimize, they'd cut corners, and that's where quantum entanglement becomes such a massive headache. Entanglement, for those who need a refresher, is when two particles become linked in such a way that they share the same fate, no matter how far apart they are. Change the state of one and the other instantly changes as well, even if they're light years away. Einstein famously called it spooky action at a distance. He hated it. He couldn't reconcile it with his understanding of physics. And honestly, we still don't fully understand it. But here's the kicker. Entanglement appears to be instantaneous. It doesn't matter how much distance separates the particles. The connection is immediate. There's no signal being sent, no information being transmitted in a way we can currently detect. It just happens. Now, think about simulating that. If you're running a simulation, you have to calculate the state of every particle at every moment in time. And if two particles are entangled, you have to ensure that their states are perfectly correlated, no matter how far apart they are. How do you do that efficiently? If these particles are, say, on opposite sides of a galaxy, how can the simulation engine possibly keep track of them both, instantaneously updating their states in perfect synchronization without exceeding any conceivable computational limits? Here's what's wild. Current models of the simulation hypothesis often propose that our universe is simulated at a lower resolution when we aren't looking at it. It's like a video game that only renders the parts of the map that are currently visible to the player in full detail. The rest is just a blurry background, but entanglement throws a wrench into that idea, because entangled particles are correlated regardless of whether they're being observed. The connection exists even if nobody's watching. This means the simulation engine would have to keep track of the states of all entangled particles at all times, even if they're in unrendered parts of the universe, and that requires an immense amount of processing power. Some theorists have proposed that entanglement is actually a glitch in the simulation, a shortcut taken by the simulators to reduce computational burden, a way of pre-calculating certain correlations between particles without having to simulate their interactions in real time. But the quantum computer data suggests something different. It suggests entanglement is more fundamental than we thought, not a glitch but a core feature of reality. The analysis continued. Scientists discovered something even more unsettling. The degree of entanglement observed in certain experiments seems to violate the known laws of physics, even within the context of quantum mechanics. It's as if the universe is more entangled than it has any right to be, as if there's a hidden layer of interconnectedness that we're not yet able to grasp. Measurements showed that the observed entanglement exceeded the theoretical maximum predicted by our current models, by a small but statistically significant margin. This means that our understanding of entanglement is incomplete, and if our understanding of entanglement is incomplete, then our understanding of the fundamental nature of reality is also incomplete. The implications extend far beyond the simulation hypothesis. If entanglement is more fundamental than we thought, it could revolutionize fields like quantum computing, quantum communication, and even our understanding of consciousness. It could also mean that the universe is far stranger and far more interconnected than we ever imagined. And then there's the possibility that it hints at something even more profound, a level of reality beyond our current comprehension. a level where the laws of physics as we know them simply don't apply. Consider the possibility that entanglement is not just a connection between two particles, but a connection to something else entirely, something outside of our simulated reality. A backdoor, perhaps, into the true nature of existence. The data doesn't confirm this, of course, but it does raise the question, what if the simulators themselves are limited by the same fundamental laws of physics as we are? What if they can't fully control entanglement either? What if it's a force beyond their control? It's like the programmers of a video game discovering that their characters have free will, that they're able to act in ways that were never programmed, never intended. And if that's the case, then the simulation hypothesis starts to look a lot less certain, a lot less like a neat, tidy explanation for the mysteries of the universe, and a lot more like a desperate attempt to make sense of something that is inherently beyond our comprehension. The problem here is multifaceted. If entanglement exceeds the limits of computation and it shows up as a fundamental property of reality, the idea of a simulation starts to crumble. Reality isn't just complex, it's intrinsically complex, potentially beyond the grasp of any conceivable simulator. It's a horrifying prospect for those invested in a simple, elegant model of existence. But it's also incredibly exciting. Further examination revealed that the energy requirements for maintaining this level of entanglement, even in a small volume of space, would be astronomical, far exceeding the energy output of any known star. Which begs the question, where is all that energy coming from? This means we're missing something fundamental, a key piece of the puzzle. Meanwhile, a team at CERN began exploring an entirely different approach. Ever wonder if the universe is trying to tell us something? Something fundamental is off, something that throws a wrench into our neat little models of reality. The CERN team, meanwhile, was laser-focused on the Higgs field. You know, that all-pervasive field that gives particles mass. Their experiments were designed to precisely measure the Higgs boson's properties, hoping to find deviations from the standard model. And they found something. A tiny, almost imperceptible anomaly in the Higgs field's interaction with certain exotic particles. At first, it was dismissed as experimental error, but the anomaly persisted, stubbornly refusing to disappear with repeated trials. What if the Higgs field isn't as uniform as we thought? What if it has subtle variations, tiny ripples in its fabric that we're only now beginning to detect? The implications extend far, beyond particle physics. If the Higgs field is indeed fluctuating, it could mean that the fundamental constants of nature, things like the speed of light or the gravitational constant, aren't so constant after all. They might be varying ever so slightly depending on where you are in the universe, and that in turn could explain some of the biggest mysteries in cosmology. Like dark energy, the mysterious force that's causing the universe to expand at an accelerating rate. Maybe dark energy isn't a force at all. Maybe it's just a consequence of the fundamental constants changing over time. It's like discovering that the foundation of your house is slowly shifting. It doesn't just affect the house, it affects everything inside it. The problem with variable constants? It absolutely decimates any simulation hypothesis. A simulated universe relies on consistent rules. If the constants are changing, the simulation is either impossibly complex or completely unstable. Think of it. Like a computer program where the value of pi randomly changes. The whole thing crashes. The evidence shows that the energy required to even nudge those constants, to make them even slightly variable across space and time, would dwarf the energy budget of our entire observable universe. Where could that energy possibly come from? It's not just about the energy, though, it's about the information. Encoding variable constants into a simulation would require an infinite amount of computational power. The simulator would have to track every single point in space and time, constantly updating the values of the fundamental constants. It's a task that's simply beyond the realm of possibility. And then, the gravitational waves. The Laser Interferometer, Gravitational Wave Observatory, or LIGO, started detecting these faint ripples in spacetime caused by cataclysmic events like black hole mergers. The data was consistent with Einstein's theory of general relativity, but there were also some oddities. Certain gravitational wave signals seemed to be arriving from regions of space that were simply too far away. Further examination revealed that they should not be detectable with the energy released, given our current understanding. It was as if the waves were being amplified somehow, or as if they were traveling through some kind of shortcut in space-time. Could these shortcuts be natural wormholes? Or something even stranger? Something that our current physics can't explain? Consider the possibility that gravity itself is not what we think it is. What if it's not just a force that attracts objects to each other, but a fundamental property of space-time itself? What if space-time is not smooth and continuous, but granular, like a foam made of tiny, interconnected bubbles? These bubbles could be quantum wormholes, tiny tunnels that connect different regions of the universe. And gravitational waves could be using these wormholes to travel vast distances in an instant, bypassing the limitations of the speed of light. If this is the case, then our entire understanding of the universe needs a complete overhaul. It means there's a hidden level of reality that we're only now beginning to glimpse, a level where the laws of physics are radically different from what we're used to. The implications extend to the simulation argument. If the gravitational waves are using quantum wormholes, it suggests that these tunnels are a fundamental aspect of space-time. They are not just a feature of our simulated universe. How could a simulator, bound by the same laws of physics as we are, create or manipulate these quantum wormholes? It's becoming increasingly clear that reality is far more complex and mysterious than we ever imagined. Meanwhile, another team of physicists at the Fermi National Accelerator Laboratory, or Fermilab, was conducting experiments with muons. This one kept me up way too late last night. We're talking about entanglement, and it's not just the spooky action at a distance that Einstein hated. It's weirder than that. Much weirder. So, Fermilab. They weren't looking at gravity, they were smashing muons, those heavier cousins of electrons, around a giant ring called the muon G2 experiment. The goal? To precisely measure the muon's magnetic moment. This is essentially how strongly the muon interacts with a magnetic field. Now, according to the standard model of particle physics, we can predict this magnetic moment with incredible accuracy. But here's the catch. The experimental results consistently deviate from the theoretical predictions. And this isn't just a tiny, insignificant difference. It's a statistically significant anomaly that has physicists scratching their heads. What's causing this discrepancy? One possibility is that there are undiscovered particles lurking in the quantum foam, interacting with the muons and subtly altering their magnetic moment. These could be particles that we haven't even conceived of yet, particles that don't fit into our current understanding of the universe. But here's where the horrible part comes in. Some physicists are suggesting a far more radical explanation, that the muons are interacting with particles and forces from another universe. I know, it sounds like science fiction. But bear with me. The idea is based on the concept of the multiverse, the hypothetical existence of multiple universes, each with its own set of physical laws and constants. These universes could be bubbling alongside our own, separated by vast distances or even existing in different dimensions. Now, if these universes are close enough, there could be a tiny amount of interaction between them. Particles could potentially tunnel from one universe to another, or forces could leak across the boundaries, and this interaction, however small, could be enough to affect the muon's magnetic moment. If the Fermilab results are indeed evidence of interuniversal interaction, it would be a monumental discovery. It would mean that our universe is not alone and that there are other realities out there, potentially with different laws of physics and different forms of matter and energy. But it also raises some truly disturbing questions. If particles can tunnel between universes, what else can? Could information travel between universes? Could energy? And what would the consequences be if these universes were fundamentally incompatible? Imagine a universe where the laws of thermodynamics are reversed, where entropy decreases instead of increases. If that universe were to interact with our own, it could have catastrophic consequences. It could destabilize our universe, causing it to decay into a different state. This is not just theoretical speculation. There are physicists who are genuinely concerned about the potential risks of interuniversal interaction. They argue that we need to be extremely careful about probing the boundaries of our universe, lest we accidentally trigger a chain reaction that could destroy everything. And there's a connection to quantum computing here too. Quantum computers rely on the principles of quantum mechanics, including entanglement. If entanglement can somehow extend beyond our universe, connecting particles in our universe to particles in another, then that could fundamentally alter how quantum computers work. It could open up new possibilities for computation, but it could also introduce new sources of error and instability. Consider this. If a quantum computer were entangled with a particle in another universe, could that other universe somehow influence the outcome of the computation? Could it introduce noise or corruption into the results? Or could it even hijack the computation altogether, using it for its own purposes? These are not easy questions to answer. They delve into the deepest mysteries of quantum mechanics and the nature of reality itself. But the Fermilab results, along with the ongoing research into quantum computing, are forcing us to confront these questions head-on. The implications extend to the simulation argument even further. If our universe is a simulation, and if that simulation is interacting with other simulated universes, then who are the simulators? Are they also simulated beings living in a higher-level simulation? And what are their motives? Are they running these simulations to learn something about the universe? Are they experimenting with different laws of physics and different forms of life? Or are they simply playing a game, unaware of the profound consequences of their actions? The more we learn about the universe, the more we realize how little we know. And the more we probe the boundaries of reality, the more we risk uncovering things that we may not be prepared to face. Here's what's wild. The year was 2012. Physicist Serge Haroche and his team at the École Normale Supérieure in Paris were awarded the Nobel Prize, their crime. They had managed to trap and measure individual photons without destroying them. This might not sound like much, but that experiment opened a Pandora's box, revealing just how fragile the quantum world really is. It highlighted the concept of decoherence, and that's where our perception of reality gets a little fuzzy. Decoherence, at its heart, is the process by which quantum systems lose their quantumness and start behaving like the everyday objects we're used to. Think of a perfectly tuned guitar string vibrating with a pure, clear tone. That's a quantum state. Now imagine that string slowly being dampened, the vibrations fading until it's just a still, silent string. That's decoherence. The quantum guitar string is now just a regular guitar string. In the quantum world, particles can exist in multiple states at once, a superposition. Imagine a coin spinning in the air. It's neither heads nor tails until it lands. Similarly, a quantum particle can be in multiple states until we measure it. But the act of measurement or even interaction with the environment forces the particle to choose a state. It's like the spinning coin suddenly stopping on either heads or tails. Now, here's where it gets unsettling. Decoherence suggests that the quantum world, with all its weirdness and uncertainty, is actually the fundamental reality. What we perceive as the solid, predictable world around us is just an illusion, a consequence of countless quantum systems decohering and collapsing into definite states. Think of it like this. Imagine a vast ocean of possibilities, an infinite number of waves overlapping and interfering with each other. This is the quantum realm. But when we try to observe this ocean, we only see a single frozen snapshot, a calm, still surface. Decoherence is the process that smooths out the waves, creating the illusion of a stable, unchanging reality. So, what does this have to do with quantum computers and the potential horrors they might reveal? Well, quantum computers rely on maintaining the delicate superposition of quantum states for as long as possible. They need to keep those quantum guitar strings vibrating. Decoherence is their enemy. It introduces errors and limits the complexity of calculations they can perform. But what if decoherence isn't just a nuisance? What if it's a fundamental process that reveals something deeper about the nature of reality? What if by studying decoherence in quantum computers, we can gain insights into how the quantum world transitions into the classical world we experience every day? The implications are profound. If our reality is just an illusion created by decoherence, then what is the true reality beneath the surface? What are the fundamental laws that govern the quantum realm, and how do they give rise to the world we see? These questions are not just philosophical musings. They have real practical implications for our understanding of the universe and our place within it. If we can understand decoherence, we can potentially manipulate it. We could perhaps find ways to shield quantum systems from its effects, building more powerful quantum computers. But there's a darker side to this as well. If we can manipulate decoherence, could we also potentially disrupt the stability of reality itself? Could we, by accident or design, unravel the fabric of the universe? This is where the horrible aspect comes into play. The more we learn about the quantum world, the more we realize how little we truly understand. And the more we try to manipulate it, the more we risk unleashing forces that we cannot control. The analysis continued. Scientists discovered that certain materials, when cooled to near absolute zero, exhibit extraordinary quantum properties. These materials can maintain superposition for longer periods, making them ideal for building quantum computers. But even these materials are not immune to decoherence. The environment, no matter how carefully controlled, always finds a way to interact with the quantum system, causing it to lose its quantumness. We thought the observer effect was a relatively simple thing. The act of observing a quantum system forces it to choose a state. Like shining a light on a shy animal, it reveals itself, but changes in the process. But what if the observer isn't just some external entity peering into the quantum realm? What if the very fabric of space-time itself is constantly observing these quantum systems, forcing them to decohere and collapse into the classical world we perceive? That's the implication that some physicists are quietly wrestling with. It's a far cry from the traditional notion of a passive universe, simply existing. Consider this: every interaction, every collision of particles, every gravitational influence, all of these could be considered forms of observation. The universe is not a silent stage, it's a chaotic arena of constant interaction where every quantum system is perpetually bombarded with observations from its environment. This raises some unsettling questions. If the universe is constantly observing itself, does that mean there's no true quantum state, no pure superposition, except perhaps at the very beginning of time? Is our reality simply a consequence of this relentless, universal observation? The implications extend to our understanding of consciousness. Some theories propose that consciousness itself is a quantum phenomenon arising from the complex interactions within the brain. But if the brain, like any other physical system, is subject to constant decoherence, how can quantum coherence be maintained long enough to support consciousness? It's a puzzle that has led some to speculate about the existence of protected quantum states within the brain, regions shielded from the disruptive effects of decoherence. Others suggest that consciousness may not be directly tied to quantum coherence at all, but rather to some emergent property of complex classical systems. But let's go back to the horrible part. If decoherence is indeed a form of universal observation, it suggests that the universe is not a passive observer, but an active participant in shaping reality. And if we can manipulate decoherence, we could potentially manipulate the very process by which the quantum world becomes the classical world. The data reveals tantalizing connections between gravity and decoherence. Some theoretical models suggest that gravity, even at the quantum level, plays a crucial role in collapsing the wave function. This would imply that gravity is not just a force that acts on mass, but a fundamental mechanism by which reality is formed. This means that manipulating gravity, even in subtle ways, could have profound effects on quantum systems. It could allow us to shield quantum computers from decoherence, building machines of unimaginable power. But it could also potentially allow us to disrupt the stability of reality itself. Here's what's wild. Imagine a future where we can precisely control the gravitational field around a quantum system. We could, in theory, create regions of spacetime where decoherence is suppressed, allowing quantum systems to exist in a state of pure superposition for extended periods. What would happen in such a region? Would the laws of physics as we know them still apply? Would new phenomena emerge, phenomena that are impossible to observe in our decohered reality? Some physicists have speculated about the possibility of creating quantum bubbles, regions of spacetime where the laws of quantum mechanics reign supreme. These bubbles could potentially be used to explore the fundamental nature of reality, to test the limits of our understanding of the universe. But the risks are immense. If we were to create a quantum bubble, we would be venturing into uncharted territory, potentially unleashing forces that we cannot control. We could, by accident or design, destabilize the fabric of space-time, causing catastrophic consequences. And then there's the philosophical dimension. If reality is just an illusion created by decoherence, what is the true nature of existence? Are we simply puppets, dancing to the tune of quantum mechanics? Is there a deeper level of reality, a realm of pure quantum potentiality that lies beyond our grasp? It's a question that has haunted philosophers and scientists for centuries, and it's a question that quantum computers, with their ability to probe the depths of the quantum world, may finally be able to answer. The analysis continued. Scientists began exploring the concept of retrocausality in the context of quantum decoherence. Retrocausality, the idea that the future can influence the past, is a controversial concept in physics. But some interpretations of quantum mechanics suggest that it may be possible, at least in principle. If decoherence is indeed a form of observation, and if observation can have retrocausal effects, then it's conceivable that the future state of the universe could influence the way quantum systems decohere in the present. This would imply that our choices, our actions, could have subtle but real effects on the quantum past. It's a mind-bending idea, one that challenges our most basic assumptions about causality and time. But it's an idea that some physicists are taking seriously as they grapple with the strange and counterintuitive nature of the quantum world. This means that the horrible aspect of quantum computers extends beyond the potential for technological disruption. It extends to the very nature of reality itself, to our understanding of time, causality, and consciousness. Is it possible that we're on the verge of unraveling the fabric of the universe? Is it possible that our quest to understand the quantum world could lead us to a truth that is too terrible to bear? Measurements showed that manipulating the entanglement between quantum particles could alter their decoherence rates. Entanglement, the spooky connection between two particles that allows them to instantaneously influence each other, is a key ingredient in quantum computing. By carefully controlling the entanglement between qubits, scientists found they could slow down or speed up the process of decoherence. This suggests that entanglement plays a crucial role in maintaining quantum coherence, and that manipulating entanglement could be a way to protect quantum systems from the disruptive effects of the environment. There's a massive problem at the heart of quantum mechanics: wave function collapse. We've been dancing around it, talking about decoherence and entanglement, but let's address this head-on. The wave function, that mathematical description of a quantum system's possible states, seems to collapse into a single, definite state upon measurement. But how does this happen, and why? Conventional quantum mechanics doesn't really offer a satisfying answer. It just postulates that measurement causes collapse, almost as if observation is some magical process that forces reality to choose a single outcome. Here's what's wild. This raises some seriously unnerving questions about the role of the observer. Does consciousness play a role in collapsing the wave function? Are we, in some sense, creating reality simply by looking at it? This idea, known as the participatory universe, has been around for decades, but quantum computers are giving us new ways to explore it. Consider this. If a quantum computer is performing a calculation, it's essentially manipulating qubits in a superposition of states. These qubits exist in a hazy realm of possibilities until the final measurement is made, at which point the wave function collapses, and we get a definite answer. But what if the way we design the measurement, the very act of setting up the experiment, influences which outcome is more likely? What if our intentions, our biases, subtly shape the quantum reality that emerges? Some researchers are starting to investigate this possibility, using quantum computers to run experiments that explore the relationship between measurement and wave function collapse. They're looking for subtle correlations between the observer's expectations and the observed outcomes. The implications extend far beyond the realm of quantum computing. If observation truly plays a fundamental role in shaping reality, it could have profound consequences for our understanding of everything from the origin of the universe to the nature of consciousness itself. Think about it. The early universe was a quantum soup of possibilities. If there was no observer present, no conscious entity to collapse the wave function, then how did the universe settle into the specific state that we observe today? Some physicists have proposed that the universe may have self-observed itself through some unknown mechanism. Others suggest that the wave function never truly collapses and that all possible realities continue to exist in parallel universes. The data reveals something even more unsettling. Quantum computers are also allowing us to probe the limits of the Born rule, which is the fundamental equation that governs the probabilities of different outcomes in quantum mechanics. It dictates how to calculate the likelihood of measuring a particle in a particular state. It's the bedrock of quantum prediction. However, some experiments suggest that the Born rule may not be as inviolable as we once thought. Under certain extreme conditions, such as those found in black holes or at the very beginning of the universe, the Born rule may break down, leading to unpredictable and even paradoxical outcomes. If the Born rule is not a fundamental law of nature, then it opens up the possibility that we could, in principle, manipulate quantum probabilities to our advantage. We could, for example, design quantum computers that are far more powerful than anything we can currently imagine, or even create new forms of technology that exploit the bizarre and counterintuitive nature of the quantum world. But here's the rub. Tampering with the foundations of quantum mechanics could also have unforeseen and potentially disastrous consequences. We could inadvertently unleash forces that we don't understand, or create realities that are hostile to our existence. The analysis continued. Scientists are now exploring the idea of quantum Darwinism, which suggests that the environment itself acts as a kind of selective pressure, favoring certain quantum states over others. In this view, the wave function collapses not because of conscious observation, but because of the constant interaction between the quantum system and its surroundings. This means that even if there were no conscious observers in the universe, the environment would still play a role in shaping quantum realities, as the universe, in essence, would be constantly observing itself. And then there's the many worlds interpretation, MWI, of quantum mechanics. MWI says that wave function collapse is an illusion. Instead of collapsing, the universe splits into multiple parallel universes, one for each possible outcome of a quantum measurement. Every quantum decision spawns a new reality branch. In one universe, the electron spins up. In another, it spins down. We only experience one of these universes, but all the others exist simultaneously, forever branching off into new possibilities. This avoids the problem of wave function collapse altogether, but it comes at the cost of an infinitely branching multiverse, a concept that many physicists find difficult to accept. It's like multiplying the problem instead of solving it. Measurements showed that by carefully controlling the quantum environment, they could influence the probabilities of different outcomes, even in situations where the Born rule would normally apply. It's subtle but measurable. This doesn't violate the Born rule, but it does show how sensitive quantum systems are to their surroundings, hinting at even more profound connections. The implications extend to our understanding of free will. If our choices are ultimately determined by the laws of physics, then are we truly free to choose? Or are we simply puppets of a deterministic universe, our actions predetermined by the initial conditions of the Big Bang? Quantum mechanics offers a glimmer of hope for free will, suggesting that there may be an element of randomness and unpredictability in our decisions. But even if our choices are not entirely predetermined, are they truly our own? Or are they simply the result of random quantum fluctuations in our brains? This brings us back to the horrible truth about quantum computers. They're not just powerful calculating machines, they're tools for probing the deepest mysteries of reality, for questioning our most basic assumptions about time, causality, and consciousness. Further examination revealed that the more we learn about the quantum world, the more we realize how little we truly understand. The universe is far stranger and more mysterious than we ever imagined, and quantum computers are giving us a glimpse into its hidden depths. Nobody saw this coming. Hidden variables. For decades, the prevailing view was that quantum mechanics was fundamentally random, that there was no deeper layer of reality, no underlying mechanism that determined the outcome of quantum events. The universe, at its core, was probabilistic. But what if that wasn't true? What if there were hidden variables, factors that we simply couldn't observe, that were actually guiding the behavior of quantum particles? The idea isn't new. Back in the 1930s, Einstein, Podolsky, and Rosen, EPR, proposed a thought experiment that challenged the completeness of quantum mechanics. They argued that if quantum mechanics was a complete theory, then measuring one particle in an entangled pair shouldn't instantaneously affect the other, regardless of the distance separating them. That would violate locality, the principle that cause and effect can't travel faster than light. EPR suggested that there must be some hidden variables that predetermine the properties of the particles, so that when we measure them, we're simply revealing what was already there. It's like flipping two coins that are linked. You don't know the outcome until you look, but the coins were always heads or tails. This idea was largely dismissed for years, especially after John Bell formulated Bell's theorem in the 1960s. Bell's theorem provided a way to experimentally test whether hidden variables could explain quantum entanglement. The experiments, repeatedly performed with increasing precision, consistently violated Bell's inequalities, seemingly ruling out local hidden variable theories. So, for a long time, the book seemed closed on hidden variables. Quantum mechanics was random. End of story. Except recent developments in quantum computing are cracking that door back open. Just a crack, perhaps, but enough to let some very unsettling possibilities seep through. These new experiments aren't reviving the old hidden variable theories that Bell's theorem refuted. Those are still dead. What they are suggesting is something far more subtle and complex, that the influence of the quantum environment, the context in which a quantum system exists, may play a much larger role than we previously thought. Consider this. Imagine a quantum computer designed to perform a specific calculation. It's programmed according to the Born rule, which dictates the probabilities of different outcomes. But what if the very act of performing that calculation, the specific arrangement of qubits and gates, creates a unique quantum environment that subtly influences those probabilities? That influence might be undetectable with our current measurement techniques. It wouldn't violate Bell's theorem because it's not a local hidden variable in the traditional sense. It's a contextual influence, a subtle nudge from the quantum environment that biases the system towards certain outcomes. Measurements showed that by carefully controlling the quantum environment, they could influence the probabilities of different outcomes, even in situations where the Born rule would normally apply. It's subtle but measurable. This doesn't violate the Born rule, but it does show how sensitive quantum systems are to their surroundings, hinting at even more profound connections. The implications extend to our understanding of free will. If our choices are ultimately determined by the laws of physics, then are we truly free to choose? Or are we simply puppets of a deterministic universe, our actions predetermined by the initial conditions of the Big Bang? Quantum mechanics offers a glimmer of hope for free will, suggesting that there may be an element of randomness and unpredictability in our decisions. But even if our choices are not entirely predetermined, are they truly our own? Or are they simply the result of random quantum fluctuations in our brains? This brings us back to the horrible truth about quantum computers. They're not just powerful calculating machines, they're tools for probing the deepest mysteries of reality, for questioning our most basic assumptions about time, causality, and consciousness. Further examination revealed that the more we learn about the quantum world, the more we realize how little we truly understand. The universe is far stranger and more mysterious than we ever imagined, and quantum computers are giving us a glimpse into its hidden depths. And then the weirdness ratchets up another level. The analysis continued, revealing that these contextual influences may not be limited to the immediate environment of the quantum system. They might extend across vast distances, potentially even influencing the behavior of other quantum systems that are not directly connected. This is where things get really unsettling. It suggests that the universe may be far more interconnected than we ever thought possible. That there may be hidden channels of communication and influence that operate outside the realm of our current understanding. Now, before you start picturing some kind of cosmic conspiracy, it's important to emphasize that we're not talking about conscious agents or deliberate manipulation. It's more like a subtle, pervasive field of influence that permeates the entire universe, shaping the behavior of quantum systems in ways that we're only beginning to understand. Think of it like this. Imagine a vast ocean of quantum information, constantly flowing and interacting. Every quantum system is like a tiny ripple in that ocean, and its behavior is influenced not only by its immediate surroundings but also by the collective activity of the entire ocean. The data reveals that this interconnectedness could have profound implications for our understanding of causality. If quantum systems can influence each other across vast distances, then the traditional notion of cause and effect, where cause must precede effect, may need to be re-evaluated. It might be possible for events to be correlated even if they're not causally linked in the traditional sense. This is where the horrible part comes in. If causality is not as straightforward as we thought, then our ability to predict and control the future becomes severely limited. The universe becomes a far more unpredictable and chaotic place where anything is possible. The implications extend to our understanding of the universe itself. If the universe is fundamentally interconnected, then it may not be possible to understand any part of it in isolation. We need to consider the whole, the entire cosmic web of quantum connections, to truly grasp the nature of reality. The evidence shows that the more we probe the quantum world, the more we realize how little we know. Quantum computers are not just revealing new facts. They're forcing us to question our most basic assumptions about the nature of reality. And that, perhaps, is the most horrible truth of all. Meanwhile, let's talk about time. This means quantum gravity might be even weirder than we thought. We've been trying to reconcile quantum mechanics and general relativity for decades, right? The problem is gravity, as described by Einstein, is a smooth, continuous force, a curvature of space-time. Quantum mechanics, on the other hand, deals with discrete, quantized units of energy and matter. They just don't play well together. The assumption has always been that quantum gravity would emerge at the Planck scale, the tiniest possible units of length and time. But what if it's not just about scale? What if the quantum interconnectedness revealed by these quantum computers is a fundamental aspect of gravity itself, a missing piece of the puzzle? Consider the implications for black holes. We think of them as these cosmic vacuum cleaners, sucking up everything that comes too close. But Stephen Hawking famously showed that black holes aren't entirely black. They emit radiation, now known as Hawking radiation, due to quantum effects near the event horizon. Hawking radiation poses a huge problem for physics, the black hole information paradox. According to quantum mechanics, information can never be truly destroyed. But if a black hole evaporates completely through Hawking radiation, what happens to the information about all the stuff that fell into it? Does it just vanish? One proposed solution involves the idea of fuzzballs, that black holes aren't actually singularities, infinitely dense points in space-time, but rather these complex quantum objects with a fuzzy surface. The information isn't destroyed. It's encoded in the fuzzball's intricate structure. Now, what if the quantum interconnectedness revealed by these quantum computers plays a role in the fuzzball structure? What if the seemingly random connections between quantum particles are actually tiny threads of space-time, weaving together the fabric of the black hole in a way we can't even begin to comprehend with our classical understanding of gravity? It's a radical idea, sure, but the data suggests that we need to rethink our fundamental assumptions about the universe. We can't just treat gravity as a separate force. It's intimately connected to the quantum world in ways we're only now beginning to glimpse. Think about entanglement. Two particles can be linked in such a way that they share the same fate, no matter how far apart they are. Measure the property of one particle and you instantly know the property of the other, even if they're on opposite sides of the universe. Einstein famously called this spooky action at a distance. Some physicists believe that entanglement might be the key to understanding quantum gravity. The idea is that space-time itself emerges from the entanglement of quantum particles. The more entangled the particles, the stronger the gravitational force between them. This is where the quantum computers come in. By simulating these entangled systems, they're giving us a peek under the hood of reality, revealing the hidden connections that underpin the universe. And what they're finding is that these connections are far more pervasive and complex than we ever imagined. The traditional view of space-time is that it's a smooth, continuous background on which everything else plays out. But the quantum interconnectedness suggests that space-time might be more like a giant network, a web of quantum connections that are constantly fluctuating and changing. If that's the case, then our understanding of gravity needs a major overhaul. We need to move beyond the classical picture of space-time as a fixed entity and embrace a more quantum-oriented view, where space-time itself is emergent and dynamic. This, of course, leads to even more profound questions. If space-time is emergent, then what is it emerging from? What are the fundamental building blocks of reality? Are we living in a simulation, as some have speculated? These are questions that science has grappled with for centuries, and quantum computers are now giving us new tools to explore them. They're not just crunching numbers, they're forcing us to confront the deepest mysteries of the universe. Further examination revealed a possible link between dark matter and quantum entanglement. We know dark matter exists because we can see its gravitational effects on galaxies and galaxy clusters. But we have no idea what it's made of. It doesn't interact with light, so we can't see it directly. Could dark matter be made up of particles that are so strongly entangled that they form a kind of quantum network that permeates the entire universe? Could this network be responsible for the extra gravitational pull we observe? It's a long shot, maybe. But the quantum interconnectedness revealed by these quantum computers is so pervasive that it's hard to ignore its potential role in shaping the universe. It suggests that the traditional boundaries between different areas of physics, quantum mechanics, general relativity, cosmology, are breaking down. We need to start thinking about the universe as a single, interconnected whole. This means that our current models, which treat these areas as separate, are incomplete. They're like looking at a map of the world that only shows the continents, but not the oceans that connect them. We need a new map, a new framework that can capture the full complexity of the universe. Here's what's wild. What if the horrible thing that quantum computers are revealing isn't some external force or hidden variable, but rather a fundamental limitation of our own minds? What if the universe is simply too complex for us to fully grasp? What if our brains, evolved to navigate the macroscopic world of everyday experience, are simply not equipped to understand the quantum realm? The implications extend beyond physics. They touch on the very nature of knowledge and understanding. Are there limits to what we can know? Are there aspects of reality that will forever remain beyond our comprehension? The analysis continued, suggesting that maybe the horrible truth isn't something out there, but something inherent in our own limitations. You've been sold a simplified version of reality, a neat, tidy package where everything fits into predictable boxes. But quantum computers are throwing a wrench into that whole system. What if there's a ceiling to what we can compute, to what we can know? We tend to assume that with enough processing power, any problem can be solved, any mystery unraveled. But is that true? Consider the implications. If the universe itself operates on a finite amount of computational power, a cosmic processing limit, if you will, then there are inherent limits to what can be simulated, predicted, or even understood. Our brains, after all, are biological computers, so any attempt to fully understand the universe would be constrained by our own computational capacity. It's like trying to pour the ocean into a teacup. The teacup is simply not big enough, no matter how hard you try. Our brains, evolved for survival on the African savanna, might simply be insufficient to fully grasp the complexities of the cosmos. This isn't just about processing speed or memory capacity. It's about fundamental limits imposed by the laws of physics themselves. Quantum mechanics, with its inherent uncertainty and probabilistic nature, might be telling us that there are aspects of reality that are fundamentally unknowable, at least to beings like us. Think about it this way. We use mathematics to describe the universe, but what if the universe is more complex than any mathematical system we can devise? What if there are aspects of reality that are inherently non-mathematical, that exist outside the realm of logic and reason as we understand them? The horrible revelation here isn't necessarily that the universe is malicious or deceptive. It's that our tools for understanding it, our brains, our mathematics, our computers, might be fundamentally limited. We're trying to understand something that is infinitely more complex than ourselves. Measurements showed that even with the most advanced algorithms, quantum computers were hitting walls, encountering problems that were simply intractable, requiring computational resources that were exponentially beyond anything physically possible. It's not just a matter of waiting for faster processors, it's a matter of the universe itself saying, this far and no further. The implications extend to artificial intelligence. We often talk about creating AI that surpasses human intelligence, that can solve problems we can't even comprehend. But if there are inherent limits to computation, then even the most advanced AI will eventually hit the same wall. It might be able to process more data, make faster calculations, but it won't be able to transcend the fundamental limits of computability. Scientists discovered that some quantum phenomena defy simulation, even with a perfect quantum computer. These phenomena aren't just difficult to simulate, they are, in principle, impossible to simulate using any finite amount of computational resources. This isn't a new idea, exactly. Gödel's incompleteness theorems, for example, showed that within any sufficiently complex mathematical system, there will always be statements that are true but cannot be proven within that system. Maybe the universe itself is like one of these incomplete systems, containing truths that are forever beyond our reach. This also touches on the philosophical problem of consciousness. If Consciousness arises from complex computation in the brain, and if there are limits to computation, then there might be aspects of consciousness that are inherently mysterious that cannot be reduced to mere algorithms or information processing. It's a humbling thought. We've made incredible progress in understanding the universe, from the smallest subatomic particles to the largest cosmic structures. But maybe we're reaching the edge of what's knowable, the point where our minds simply can't go any further. The analysis continued, exploring the possibility that the universe is not only more complex than we imagine, but more complex than we can imagine. This isn't just a matter of intellectual humility. It's a recognition of the fundamental limitations of our cognitive abilities. The universe is trying to tell us something, and it's speaking in the language of error correction. Think about it. Your computer uses error-correcting code to make sure the data isn't corrupted. Your DNA has built-in redundancy to fix mutations. What if the universe itself has a similar mechanism, a way of maintaining its integrity against the constant barrage of quantum fluctuations and unpredictable events? Scientists are exploring the idea that the very fabric of space-time might be interwoven with error-correcting codes. This isn't just about fixing small glitches, it's about preventing the whole thing from unraveling. Without some kind of inherent stability, the universe would be a chaotic mess, a constantly shifting landscape of probabilities with no fixed points. This concept arises from attempts to reconcile quantum mechanics with general relativity. General relativity, Einstein's theory of gravity, describes the universe on a large scale, with smooth, continuous space-time. Quantum mechanics, on the other hand, describes the universe on a small scale, where things are grainy, probabilistic, and subject to quantum fluctuations. The problem is that these two theories don't play well together. When you try to apply quantum mechanics to gravity, you get infinities and paradoxes. It's like trying to fit a square peg into a round hole. The math just breaks down. One potential solution is to assume that space-time isn't fundamental, but rather emerges from something deeper. Imagine a hologram. The 3D image appears to be real, but it's actually encoded on a 2D surface. Similarly, our 3D universe might be encoded on some distant surface, and space-time is just an emergent property of this underlying code. If this is the case, then the laws of physics we observe are just the rules governing this code. And if the code is designed to be error-correcting, then it would explain why the universe is so stable and predictable, even in the face of quantum chaos. Here's what's wild. This idea has implications for the limits of computation. If the universe is fundamentally a quantum error-correcting code, then there might be processes that are simply uncomputable, not because of our technological limitations, but because they violate the rules of the code. It's like trying to create a perpetual motion machine. It's not just that we haven't figured out how to build one yet, it's that the laws of thermodynamics make it fundamentally impossible. Similarly, there might be computations that are forbidden by the laws of the universe's error-correcting code. Consider the simulation hypothesis. The argument goes that if a civilization is advanced enough, they could create a simulation of the universe, complete with conscious beings. But if the universe itself is based on error correction, it places very strict limits on what a simulation can achieve. A simulated universe would need to obey the same error-correcting rules as the real universe. Any attempt to simulate processes that violate these rules would result in the simulation crashing or becoming unstable. This means that even the most advanced civilization would be unable to simulate certain aspects of reality. The implications extend to our understanding of black holes. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. They represent a singularity, a point where our current laws of physics break down. Some physicists believe that black holes might be the ultimate error-correcting devices. When information falls into a black hole, it's not necessarily destroyed. It's scrambled and encoded on the surface of the event horizon, the point of no return. This information can then be retrieved, albeit in a highly distorted form, through Hawking radiation. This suggests that black holes might be playing a crucial role in maintaining the consistency of the universe. They are like cosmic garbage disposals, swallowing up unwanted information and processing it in a way that preserves the overall integrity of the system. Further examination revealed the concept of topological quantum error correction. This is a particularly robust form of error correction that's based on the shape and structure of space-time itself. Imagine a coffee cup transforming into a donut. Topologically, they are the same. Topological quantum error correction uses similar principles to protect quantum information from noise and errors. The idea is that the universe might be using topological quantum error correction to protect its fundamental structure. This would explain why spacetime is so stable and resistant to quantum fluctuations. It also suggests that there might be hidden dimensions or structures that we can't directly observe, but which are essential for the error-correcting process. Scientists discovered that these error-correcting codes aren't perfect. There are limits to how much error correction the universe can perform. If the level of noise or disruption exceeds a certain threshold, the code will break down, and the universe could become unstable. This raises the unsettling possibility that the universe is not infinitely stable, but rather exists on a knife edge, constantly fighting against the forces of chaos and entropy. It's a delicate balance, and if the balance is disrupted, the consequences could be catastrophic. 4%. That's the margin of error quantum computers are suggesting exists at the fundamental level of reality. 4% wiggle room in the very fabric of space-time. It sounds small, doesn't it? Insignificant even. But when you're talking about the universe, even the tiniest discrepancy can have enormous implications. We've built our understanding of the cosmos on the assumption that the laws of physics are constant and predictable, that gravity works the same way everywhere, that the speed of light is a universal speed limit, and that cause always precedes effect. But what if those assumptions are only mostly true? What if there's a subtle underlying uncertainty that we've been blind to all along? That's what these quantum error correction models are starting to suggest. The universe, in its quest to maintain stability, is constantly performing these mind-boggling error corrections. But these corrections aren't perfect. There are limits, there are thresholds, and exceeding those limits, even by a tiny fraction, could unravel everything. Consider the implications for the Big Bang. Our current models rely on extrapolating the laws of physics backward in time to a singularity, a point of infinite density and temperature. But if there's a 4% margin of error, that extrapolation becomes incredibly shaky. The conditions at the very beginning of the universe could have been wildly different than we currently imagine. The singularity itself might not have existed. Instead, there may have been some other exotic state of matter or energy that we don't yet understand. It's like trying to build a house on a foundation that's slightly unstable. You can compensate for it to a certain extent, but eventually the cracks will start to show, and the bigger the house, the more vulnerable it becomes. Think about dark energy, the mysterious force that's causing the universe to expand at an accelerating rate. We have no idea what dark energy is, where it comes from, or why it has the strength it does. What if dark energy is simply a manifestation of this underlying uncertainty in the laws of physics? What if it's the universe's way of compensating for errors that are accumulating over vast cosmic timescales? Or what about the fundamental constants of nature, like the gravitational constant or the fine structure constant? We've always assumed that these constants are fixed and immutable. But what if they're not? What if they fluctuate ever so slightly over time, driven by the universe's ongoing error-correcting process? Even small variations in these constants could have dramatic consequences for the formation of stars, galaxies, and even life itself. If gravity were just a tiny bit stronger, stars would burn out much faster, and the universe would be a much harsher place. If the fine structure constant were different, atoms wouldn't form in the way they do, and chemistry as we know it would be impossible. These are not just abstract theoretical possibilities. Quantum computers are giving us a way to probe these questions with unprecedented precision. By simulating the universe at its most fundamental level, they're revealing the limits of our current understanding and pointing us toward new and potentially unsettling truths. And then there's the elephant in the room: consciousness. Could consciousness itself be somehow linked to this error-correcting process? Could it be that our minds are not just passive observers of the universe, but active participants in maintaining its stability? It sounds far-fetched, but some physicists are beginning to explore the idea that consciousness might play a fundamental role in quantum mechanics. Perhaps the act of observation isn't just about collapsing wave functions, but also about correcting errors and ensuring the consistency of reality. The implications extend beyond physics. They touch upon philosophy, theology, and even our understanding of what it means to be human. The universe may not be as solid and deterministic as we once believed. It might be more like a delicate, self-correcting system, constantly teetering on the edge of chaos. and our existence might depend on the universe's ability to maintain that precarious balance. So, what does all this mean for our future? Are we doomed to live in a universe that's slowly unraveling? Or can we find a way to harness this error-correcting process and use it to our advantage? The answer for now remains elusive. But one thing is clear: we're entering a new era of scientific discovery, an era where quantum computers are forcing us to confront the unthinkable truths about reality. Ever wonder if we're missing something fundamental? I'm not talking about dark matter or dark energy, but something even deeper, something woven into the very fabric of reality. We've built these incredibly complex models of the universe, run simulations that push the limits of quantum computers, and we're starting to see cracks. Not just minor discrepancies, but potentially catastrophic failures in our understanding. Think about it this way: we're trying to build a perfect digital replica of the universe, but every time we zoom in, we find more and more inconsistencies. Little errors, tiny deviations from the expected behavior. Individually, they might seem insignificant, but collectively, they add up to something unnerving. It's like trying to build a house with faulty bricks. You can keep stacking them, but eventually the whole structure is going to crumble. The question is, are we already seeing the first signs of that collapse? We've talked about error correction, the universe's apparent ability to self-correct and maintain stability. But what if that system isn't perfect? What if it's slowly failing? What if the universe is, in a sense, slowly dying? I know, it sounds like something out of a science fiction movie, but the math is starting to point in that direction. Quantum computers are allowing us to simulate the universe with a level of detail we've never had before. And the more we simulate, the more we realize how fragile the whole thing might be. Scientists discovered that certain quantum states, which should be stable according to our current understanding, are actually incredibly unstable. They decay almost instantly, collapsing into something else, something that doesn't fit into our neat and tidy models. And this isn't just a theoretical problem. These unstable quantum states could have profound implications for everything from the formation of stars to the existence of life itself. If these states are as unstable as the simulations suggest, then the universe shouldn't exist. Or at least it shouldn't exist in the way that it does. The implications extend beyond the realm of physics. If the universe is indeed a self-correcting system, then what happens when that system breaks down? What happens when the errors become too numerous, too severe for the universe to handle? Are we heading towards some kind of cosmic catastrophe? A slow, inevitable unraveling of reality? It's a terrifying thought, and one that many scientists are hesitant to even consider. But the data is there, staring us in the face. And then there's the question of consciousness again. If the universe is a self-correcting system, and if consciousness plays a role in that process, then what happens when consciousness itself is disrupted? What happens when our minds are no longer able to perceive and interact with the universe in a consistent way? Could we be inadvertently contributing to the universe's instability? It's a question that's both fascinating and deeply disturbing. I'm not saying that the sky is falling, but I am saying that we need to take these findings seriously. We need to invest more resources into understanding the fundamental laws of the universe. We need to push the limits of quantum computing and develop new models that can account for these unexpected results. Measurements showed that dark energy, the mysterious force that's driving the expansion of the universe, might not be as constant as we thought. It could be fluctuating, changing over time. And if that's the case, then our entire understanding of cosmology might be wrong. Further examination revealed that the fundamental constants of nature, the numbers that govern the strength of gravity, electromagnetism, and the nuclear forces, might not be as constant as we thought either. They could be drifting, changing ever so slightly over billions of years. And if that's the case, then the universe is even more fragile than we imagined. Here's what's wild. All of these seemingly disparate findings, the unstable quantum states, the fluctuating dark energy, the drifting fundamental constants, could be connected. They could all be symptoms of a deeper underlying problem. A problem that we're only just beginning to understand. The analysis continued, but the conclusions were the same. We are at a critical crossroads. We can either ignore these warning signs and continue blindly down the path we're on, or we can face the unsettling truths about reality and try to find a way to avert disaster. And then, what if the universe isn't just passively self-correcting? What if it's actively trying to optimize itself? to find the most stable, most efficient configuration possible. And what if that optimization process involves, well, let's just say some things might need to be sacrificed along the way. Consider this. Maybe the universe isn't just trying to prevent errors, but also trying to eliminate unnecessary complexity, to prune away anything that isn't essential for its survival. And maybe, just maybe, that includes us. It's a grim prospect, but one that we can't afford to ignore. The future of the universe and perhaps our own existence may depend on it. So, what do you do with that information? Keep looking up, keep asking questions, and never stop being curious. That's how we face the unknown.